Hello, y'all. Back for some more linear algebra. We'll go for about an hour and see if we can get through these examples here. So it should be showing. Right? Oh, I have to click the share button here. There we go. I think we're good now. Awesome. So let's see what we have here. Several examples, right? So example 2.4. As a simplest example of the resisted motion of a particle, find the displacement and velocity of horizontal motion in a medium in which the retarding force is proportional to the velocity. A sketch of the problem is shown in figure 2.4. The Newtonian equation F equals ma provides us with the equation of motion. So we have, so this is example 2.4. We have a projectile x is in this direction. Motion is in that direction. We have velocity v naught and a resistive force. Opposite velocity as expected. F equals kmv, since they said the resistive force is proportional to velocity, not velocity squared. And they say that the F net equals ma equals negative kmv. So it has an initial velocity, but we're assuming that it seems like gravity is causing it to accelerate. Well, I guess it's not necessarily gravity, but they told us that's the equation of motion, so that's the equation of motion. So if they tell us that's the equation of motion, then that's the left side, and kmv is on the right side, negative kmv, which is opposite the velocity. The velocity is in the direction of acceleration. All right? Not implying by this form that the retarding force depends on the mass, m. This form simply makes the math easier. So we have A equals negative kv, dv over dt equals negative kv. So 1 over v, dv equals negative k dt. We need to put all the v's on one side. We have v negative 1 dv equals negative k dt. And I'll take the integral of both of these. So we have ln v equals negative kt plus v naught. Is the integration constant, and this is 2.23, can be evaluated if we prescribe the initial condition. All right. So initial condition v at t equals 0 is defined as V naught. That means that ln V naught equals negative k at 0 plus V naught. So ln V naught equals V naught. So that means that ln V equals negative kt plus ln V naught. So E equals E of this whole thing. So that means V of t equals E negative kt E ln V naught. So that equals V naught E negative kt. And that's V of t. V of t equals V naught E negative kt. And that's equation 2.24. We can integrate this equation to obtain the displacement x as a function of time. So dx over dt equals V naught E negative kt. Dx equals V naught E negative kt dt. Integral of both sides. So xt equals V naught E negative kt. I'm going to divide by the derivative of negative kt, so that's negative k plus x. I'll just call this cx, and I'll call this cx, and I'll call this cv. So v naught is defined as v naught plus cv. So cv, cx, all right? So we'll say that x naught equals x at t equals 0. So that equals v naught over negative k plus cx. So x naught, negative x naught k over v naught. Hold up, subtract. So x naught plus v over k equals cx. See if I did that right. And if I define x naught equals 0, cx equals v over k, v naught over k. All right. This is that. So that means that x of t equals negative v naught over k e negative kt plus v naught over k. So that equals e negative kt distribute the negative, so distributed in a moment, of v naught over k plus 1. If I distribute the negative in, I don't see how that distributes like that. I have x of t equals negative v over k e to the negative kt plus v over k. Oh, see what I did wrong. So VO over K equals times uh, negative E negative KT plus 1, or we can say XT equals VO over K 1 minus E to the negative KT, which matches what the book has as equation 2.25b. This result shows that x asymptotically approaches the value v over k as t approaches infinity. Because if t in infinity, that term zeroes out. It's interesting. You could also obtain the velocity as a function of displacement by writing velocity as a function of displacement, dv over dx. The velocity as a function of displacement. So dv over dx, velocity as a function of displacement. So we have dv over dx, dt over dt. We can multiply that by 1. That becomes dv over dt, dt over dx. So this becomes dv over dt, 1 over v. So v, dv over dx equals dv over dt. dv over dt equals negative kv from up here. So v dv over dx equals negative kv. So I can cancel this and say dv over dx equals negative k. Velocity as a displacement, as a function of displacement, dv over dx. So the velocity, the change in velocity over the change in position goes as negative k, which makes sense because the drag uh, uh, component is proportional to velocity, from which we find by using the same initial conditions v velocity decreases linearly with displacement. So see how they have v equals v naught minus kx. Looking at this part here, from which we find by using the same initial conditions, v equals v naught minus kx. So this is the equation we have for v. I see. So if you were to integrate this, dv equals negative k dx. And you integrate both sides. So v equals negative kx plus v naught. So that's just another integration with v naught as the constant of integration. Therefore, the velocity decreases with displacement. dv over dx is velocity as a function of position. As displacement goes up, velocity goes down. All right. Now we have example 2.5. Find the displacement and velocity of a particle undergoing vertical motion in a medium having a retarding force proportional to the velocity. And they give us an illustration. We have the object going downward. Z. This is the height where it starts. V naught is going down. We have mg equals Fg, the force of gravity. And we have kmv equals Fr, which is the resistive force. All right. And it says the retarding force is proportional to velocity. So n equals 1 if r proportional to v. All right. We have F net equals Fg minus kmv. See if I can get this equation in the way I understand it. So if I make v naught going down positive, then F net equals mg positive minus kmv since v is negative. So ma equals mg minus kmv. M dv over dt. Actually, we could cancel the m right now. dv over dt equals g minus, actually, plus kv equals g. So now we have both sides. Notice they brought gravity. See, I won't be able to properly integrate unless dv is multiplied by that whole side. So it has to be dv over dt equals g minus kv, and dv divided by g minus kv equals dt. And then I can integrate both sides and say ln g minus kv equals t plus v, say cv, and I have to divide the left side by the derivative with respect to k. So that's divided by negative k. Which is almost what they have. We multiply the negative to the other side, which they did. And multiply the k to the other side, so O n g minus kv equals negative kt minus kcv, constant of velocity. So we can say E of this whole thing, v minus kv equals E negative kt E negative kcv. So we have negative and little freeze on my program here. Negative kv equals E negative kt E uh, minus KCV minus G. So we can say VC equals negative 1 over K E negative KT minus KCV minus or plus G over K. So if I was to try to find the constant V of 0, will be defined as V naught. So V naught equals negative 1 over K E negative KCV plus G over K. So V naught minus G over K equals negative 1 over K E negative KCV and negative V naught K plus G equals E negative KCV. So negative E of G minus VOK is E ln. Ln G minus VOK equals negative KCV. So CV equals ln G minus V naught K divided by negative uh, K. I don't know if that was worth it. Seems like it's easier just to keep the V naught there. V equals negative 1 over K. P mine is slightly different from theirs. This is matching a line. Right, so maybe they actually plug that in. Plug it in and see what happens. V of T equals negative 1 over K E negative KT E. So the negative K and the negative K balances out. So ln G minus VOK plus G over K. So that equals negative 1 over K E negative KT g minus v naught k plus g over k. Yep, it is what they have. The negative is different because I didn't put a negative on my whatchamacallit, but other than that, it matches. It's just that my negative term is different. Right. Integrating once more and evaluating the constant by setting ZT over the H. Let's look at this negative part again. It says where negative KMV represents a positive upward force. Once we take Z and VZ to be positive upward, and the motion is downward. That is, V is less than 0, so negative KMV is greater than 0. So they're saying negative mg is down. V is negative already. You have to put a negative in front of that to make it go up. Gotcha. But acceleration is downward, so the velocity is downward. So kmv will be opposite the velocity, which is negative v. We just have a v there. So we put a negative in the front. So when you put the negative v in, it becomes positive, which is upward. The counter gravity still seems odd. Right. So dx over dt equals negative equals g over k minus g minus vo k over k e negative kt. So velocity downward is positive. It is positive. This means I have to put a negative in front of the k because it's opposite direction. So mine makes sense as well. Dx equals g over k minus g minus vo k over k e negative kt dt. So I'm going to integrate both sides. We have xt equals g over k t minus g minus vo k over k e negative kt. And we're going to have to divide by the derivative of the numerator. So divided by negative k is k squared plus vx or cx. All right. And we said we're going to divide x not going to divide as x at t, which is h, equals g over is x at 0, h. So t at t equals 0, that disappears. So Gt over K is a position. K must be 1 over second. Zero on the exponential leaves us G minus V naught K over K squared plus Cx. So H minus G over V naught K over K squared equals Cx. So we have xt equals G over Kt plus G minus V naught K over K squared E negative Kt plus H minus G minus V naught K over K squared, which equals G over Kt plus H plus E plus G minus V naught K over K squared E negative Kt minus 1. I'll put it in the same form they have, and technically this would be Z, who I've defined it. I have to go back and turn all these X's into Z's. Actually, I'll just make this X. All right, so X is going down. So X of T equals H plus G over K T plus G minus V naught K over K squared E negative KT minus 1. That's equation 2.30 with the appropriate constants of um, velocity and position, not skimping on that, right? So, all right, got a pretty good handle on that. Like I said, these are long sections. And notice that mine is slightly different since I use a different convention of negatives, but all the components are exactly the same, which is good. As long as I keep my same position convention, which is the positive is down, which means velocity is positive. So I have to throw a negative in front of the term with the retarding force. Or if I make velocity negative, then there's a negative in front of velocity, both. And I have to keep the negative on the retarding term because now velocity is negative in there, and that's going to turn the whole thing positive to opposite gravity. So it doesn't matter which way we do it, unless we keep it consistent. Equation 2.29 shows that as the time becomes very long, the velocity approaches the limiting value negative g over k. Right? I'll see how that's the case, but this is called terminal velocity. See, I'm looking at a position. As velocity becomes longer, it becomes 0. Yeah, okay, I see it. So as velocity becomes longer, this term zeroes out. If t is infinity, that becomes 1 divided by infinity, which is 0. That whole thing zeroes out. So then velocity becomes the constant g over k. And mine is positive since I have the positive going downward, so it makes sense. This is called terminal velocity. So g over k is terminal velocity. Equation 2.27 yields the same result. Because the force will vanish and hence no further acceleration will occur when v equals negative g over k. G, right, see it, force is 0. So what it's saying is if v is negative g over k, and we plug this into the force, in my case, v will be g over k, since force is positive. So if v was g over k, then g over k times mk, we'll just leave gm, and mg minus gm is 0, so the force would be 0. So at maximum velocity, force is 0. There's no acceleration. It's just a constant free fall. That makes sense. At, at v equals g over k, f equals 0. Right. There's no further acceleration will occur when v equals g over k, terminal velocity. Let's write this explicitly. At t equals infinity, equals, so this is infinity. So that's in the denominator. So this whole term becomes 0. And so v infinity equals g over k. And f equals mg equals mg minus kmv equals terminal velocity. That terminal velocity equals vt. At vt, f equals mg minus km g over k equals mg minus mg, which equals 0 newtons. So at vt, no acceleration equals free fall. All right. If the initial velocity exceeds the terminal velocity in magnitude, then the body immediately begins to slow down and v approaches terminal speed from the opposite direction. Figure 2.6 illustrates these results for a downward speed. Interesting. think, because v is g over k, and this term zeroes out. The initial velocity is g over k. G over k on the left side. So the e term has to zero out, that to be true. But if v is greater than that, if v naught is greater than that, right, keep going. It's 2g over k. Let's see. If acceleration, if the initial velocity is greater than g over k, then there's a negative force, and that's a slowing down. If v naught is greater than g over k, then F net equals mg minus k m, let's say alpha g over k, which equals mg minus alpha mg equals negative. So the force is going in the opposite direction. Slowing it down. Till it reaches absolute terminal velocity. V is less than g over k, then F net equals mg minus km, we'll say beta g over k equals mg minus beta mg, which is positive. So that means that it will be accelerating. So the question is, how long would it take to reach terminal velocity from a certain speed? So I suppose I can put Vt as terminal velocity. And I can put v naught as greater than terminal velocity, and I can solve for t, and that should do it. But I'm going to do that now, so I'll keep going. All right? So example 2.6. And this will probably be our last example for now. Next, retrieve projectile motion in 2 dimensions, first without considering air resistance. Let the muzzle velocity of the projectile be v naught, naught equals muzzle v. And basically we have a projectile being projected in a projectile motion. This is theta, and here is v naught. We'll call this x. We'll call this y. Now we have movement in 2 dimensions. Retrieve the projectile also. Calculate the projectile's displacement, velocity, and range. So I think I can do this one without checking the notes. So F net, without considering air resistance, is MA. So the only force on it going to be Fg equals MA, excluding air resistance. Equals mg. Only force. There's no horizontal force. So that equals mg j plus 0 I. There's no force in the vertical. So m so dv over dt equals g dv equals g dt. Okay, integrate both sides. So vt equals gt plus cv, and v naught equals v at 0, which equals c v, since t is 0. That's going to be vc equals gt plus v naught. Dx over dt equals gt plus v naught. So dx equals gt plus v naught dt. So if I integrate both sides, we have xt equals gt squared 1/2 plus v naught t plus cx. And if we say x naught equals x at t equals 0, which we'll call 0, equals cx. Right. So that means xt equals 1/2 gt squared plus v naught t plus x naught, which is our normal equations of motion. And that's all in the y direction. In the x direction, velocity is the distance over time, which is going to be v naught since there's no forces affecting it. And distance equals velocity times time, which is going to be v naught time. So it's going to be x t, and technically this would be y t. So watch my lettering. So it's not as easy as just changing it to x since I do have a x and a y here. Equals x equals v of t. So no matter what time we take this to be in, the x will still be the same. Oh, hold up. V naught is just going to be the s component. Going to be v naught cosine theta vx of t. Vx is v naught cosine theta, just vx of t, which will not change with time. So d equals vxt equals v naught cosine theta t v naught cosine theta equals vx of t. That's the distance. Oh, equals x of t. Vx of t is just v naught cosine theta. Y. Dy is 0. This has to be a y. V naught y equals v naught sine theta. And y not equals 0. So we don't even need that there. We do have initial velocity in both directions. Y. V naught sine theta. Vox equals Vx. Let's call this Vy, make it simpler. Y. Right, so I think that's everything we need for the equations of motion. Let's see what they have. So we have using F equals mg, the force components become, so as we said, 0 in the x direction, mg equals m double dot y in the y direction. Like next thing to height of this gun, xy equals 0 initially. X Vox equals VO cosine theta. Position is T VO cosine theta. We have that. And y is 1/2 gt squared plus VOT, VYT. And we know Vy is VO sine theta, as we have here. So they have VO sine theta t, VO sine theta. Good. The speed and total displacement as functions of time are to be found. The speed and total displacement as a function of time are found to be okay, hold up here. Right. So V equals the square root of Vx squared plus Vy squared. So that equals the square root of VO cosine theta squared plus GT plus VO sine theta squared. Get the square root of all of that. So that's going to equal the square root of VO squared cosine squared theta plus G squared T squared plus 2 GT VO sine theta plus VO squared sine squared theta. So let's see what we have here. Oh, I see. They actually took position and took a derivative of it. They have to be difficult. So let's take a look at this again. So Vx is the square root of x dot squared plus y dot squared. X dot equals VO cosine theta. Y dot equals V T plus VO sine theta. It is what I had already, right? Makes sense. This is how I got that was from the integration. Well, they're doing something different here. Try this again. X dot squared equals VO squared cosine squared theta. Y dot squared equals G squared T squared plus 2G T VO squared sine squared theta plus VO squared sine squared theta. So x dot squared plus y dot squared is going to equal VO squared cosine squared theta plus G squared T squared plus 2G T VO squared sine squared theta plus VO squared sine squared theta. And we have equals. So if I were to combine these, because they both have sine squared theta, cosine, they both have VO squared. This one is sine squared, cosine squared. So we have VO squared plus GT squared plus 2GT VO squared sine squared theta. Got my squared here. That's the same thing they have, except it's like they dropped a square on their sign. So v equals the square root of this. Right? Looking at it, it's pretty much what they have. I'm already went over an hour. I'm supposed to stop at an hour. We'll finish this and then I'll end. So we can do the same thing for position, which I won't do. But we see how they got it. Our negatives are a bit different. At least seems they have dropped the square on the sign. We can find the range by determining the value of x when a projectile falls back to the ground. That is y equals 0. One is t equals t. Right? We've already calculated the range one time, even though I don't remember clearly how to do it. But perhaps I could just use a break. A good run. I shall be back later. Right now I'm on page 63. And this section has not many more pages. I may actually come back a different day. Got a lot done today. So we may come back and start from here tomorrow, and I may just come back with a different subject later so I can still get some other subjects in. So if you watch, like, and subscribe. I'll see you all next time.